Well, welcome to this webinar presented by the IET's Anglian Coastal Local Network, which represents members in Norfolk and Suffolk. Welcome also to folks from other parts of the UK and indeed globally. I'm absolutely delighted to welcome you all. I'm Kevin Foster and I'm chair of the Anglian Coastal IET Local Network, and I'll be your host for this evening. I'm absolutely delighted to introduce our speaker, Ed Friedman. Ed graduated from the University of Maryland and Wayne State University. After obtaining his PhD, he began his career in the application of space-based lasers in optics, astrophysics, oceanography, environment, climate, and defense. In his 48-year career, he has worked for several aerospace and non-profit companies, acted as a consultant to NASA and the US National Academy of Sciences. He was adjunct professor in the aerospace department of the University of Colorado, instructor in the graduate level orbital design, and has taught math and astronomy at undergraduate level. Now, Ed is the author of 4 books on optical engineering, editor of 1 book on orbital dynamics, and 1 book on energy storage technology. He holds 1 patent on space laser technology and is the author or co-author of 79 professional journals and related publications. Ed, over to you.
Thanks so much. We're going to talk about the strange business of dark energy in the universe, one of the top 2 or 3 problems that confront physics today. And let's just jump into this. So here's a sort of iconic picture of the evolution of the universe, starting from maybe quantum fluctuations, we're not absolutely sure, evolving to a much larger space that has gradually expanded in size, and somewhere about halfway through the lifetime of the universe, we see the size of the universe accelerating. And this has been a mystery for the last 20 years. Just before 2000 is when the accelerating expansion rate of the universe was detected using observations of supernova events using the Hubble Space Telescope and ground-based telescopes. And the best we can do these days is assign the acceleration to an unknown property of empty space. And these days, that property is usually referred to as dark energy. Now, in addition to, since we want to be careful to cover all the strange things going on in our universe, we also have dark matter. And it's a similarly unexplained phenomenon. We're not going to talk about that today, but it's a dark matter represents about 25% of the energy in the universe. Dark energy is a dramatically larger fraction of the energy in the universe. And if you put those 2 dark features of the universe together, all that's left is about 5%. And that's the matter that we're made of. Atoms make up only about 5% of the energy in the universe. Dark matter and dark energy are the remaining energy sources. So atomic matter makes up stars and galaxies and us and everything else that we observe. But dark matter, dark energy remain mysterious. And as I say, we're not going to talk about dark matter tonight. We're going to concentrate on the dark energy issue and how we can try to identify the origin of dark energy. Now, 100 years ago, roughly, Einstein's theory of gravity created a revolution in our understanding of the universe. And its equations were immediately digested by physicists who predicted how the universe could evolve depending on the different kinds of matter and energy that are included in the universe. Einstein himself dealt with these possible futures at a time when physicists and astronomers felt that the universe was a static structure, that the cosmos was not getting bigger or smaller. And Einstein made some efforts to use his equations to explain how a static universe could exist. Why wouldn't it collapse under the influence of gravity? And he invented various schemes for overcoming the apparent static situation that everybody embraced at that time. This was around 1917 to 1920, and gradually the technology became available for Hubble and others to show that indeed the universe is not static, it's growing. And we have much more information now because we have the benefit of space-based telescopes and gigantic telescopes compared to what existed back in the 1920s. Alexander Friedman, not related to me, a Russian, actually did calculations based on Einstein's theory of gravity and was able to show the possible evolution of the universe based on different kinds of energy that might be contained in it. Lemaitre, a Roman Catholic priest, also was engaged in this and very influential in understanding that the universe was expanding, which meant that if you ran the clock backwards, the universe that we now observe must have started from what Lemaitre called a primeval atom. That is a tiny, tiny event, physically tiny, but with enormous energy in it that birthed the universe we see today. So progress was being made starting in the 1920s, understanding whether the universe was static or dynamic. And today, as I've said in my introductory remarks, we know the universe is not only expanding, but the rate is accelerating. And the question is, what's propelling that? And dark energy is usually identified as the culprit for the accelerating expansion of the universe. And what we don't know is, what is it? So here I'm going to show you a couple of little icons of what it might be. It could be that dark energy is just an inherent property of empty space, that if you create empty space, energy spontaneously appears there. And that presence of that energy is a source of influence in the universe and causes it to expand, creating more empty space, which immediately fills with dark energy. That's what we observe happening. Why that would be the case, we don't know. There are other speculations. Among them is that dark energy is somehow associated with a universe that does not share the spatial dimensions that we observe, but somehow its properties leak into our universe. And some of you have probably read books or journal articles or magazine articles about the multiverse. That is an idea that the universe, well, let's put a capital U on that word, universe, that it's filled with universes. And we see one of them, and that there are others around us that possibly share our universe in some small way. Perhaps that's where dark energy comes from. There's also a possibility that quantum mechanics, the theory that describes the subatomic world, has some features that are not observable unless you look at the cosmos in its entirety. We've had an enormous benefit from understanding the subatomic world and our ability to build electronics and actually how we're sharing information right now using all kinds of digital technology. All is based on understanding quantum mechanics of materials and exploiting that understanding to create computer chips and communication chips and so forth. Maybe there's a feature of quantum mechanics that has to be added to our current theory so that we can include a dark energy component. It's also possible that dark energy is somehow related to an as yet unknown force of nature. Those of you who have taken physics know that we have 4 forces that are the standard and have been the standard description of the physical world for 100 years, including electromagnetism, the weak force, which moderates radioactive decay, the strong force that makes sure that atoms are stable and that protons in the nucleus of atoms don't fly away from each other. Otherwise, atoms wouldn't exist and we wouldn't exist. And lastly, the least powerful force, but the most persistent one, is gravity. So those are the 4 forces that we talk about in physics. Maybe there's one we haven't yet discovered, and it's affiliated with this mystery of dark energy. Perhaps there are particles, dark energy particles somehow, that we cannot reproduce in accelerators. Like the biggest one we have is the one in Switzerland and France at CERN. Maybe there's a family of particles that we haven't found, and dark energy is affiliated with those particles. And it's always possible that Einstein's theory of gravity is somehow incomplete. It has been tested over and over and over again in ground-based experiments, space-based experiments, and it never failed to explain what we observe. Very recently, we have new windows on the universe in the form of gravitational wave sensors, and they guarantee that Einstein's theory, as we know it, is correct. The question is it complete? And so perhaps there's a dark energy component to be added to Einstein's theory. Now, let's talk about a little terminology. In the early part of the mid-century part of the 20th century, the idea of quintessence emerged. That is a version of dark energy that could vary with time. And gradually, astronomers and astrophysicists observe in detail the expansion rate of the universe. And one explanation for what was observed was this idea that there was some sort of strange vacuum energy property to the universe that changes over time. And that was given the name quintessence. Vacuum energy is also a description of empty space, and it's a term used by quantum physicists, and we're going to see more of that during this presentation. And vacuum energy derives from quantum mechanics and the Heisenberg uncertainty principle. We'll get into that in a minute. That's another possible form. Now, Einstein, back when his theory emerged in the late 19-teens, dubbed the possibility of a cosmological constant. This was something he invented to try to assure that his theory of gravity would result in a static universe. So that's yet another term. And today we use the term dark energy. And dark energy has the following property, that no matter where we look in the universe, in no matter what direction, we see the expansion, and the rate of expansion is detected by looking at the motions of stars, principally exploding stars, supernova events. And we see the density of empty space containing energy. And that's related to the expansion that I discussed. So what dark energy does, it propels the expansion of the universe, which means the universe gets volumetrically bigger. And in the process, more energy fills the vacuum that is being created. And as the universe grows, there's more energy. And you can see why this would be kind of a runaway effect. The more dark energy there is, the bigger the universe gets, and the empty space immediately fills with more dark energy and keeps propelling this expansion. So I mentioned Lemaitre and Friedman. I'm going to show you some predictions from their equations that emerged in the 1920s. And we'll use these Greek symbols, omega m, meaning what fraction of the universe is material, and omega lambda, what fraction of the universe is dark energy. And I'll show you some graphs here in a second of how those numbers influence the future of the universe. Now, in the early universe, light was the most prominent source of energy, creating the expansion. That light has now been diluted because the universe is enormously bigger than it was in the early days, because the universe was physically small in the early days of its life. And there was also energy invested in the curvature of the universe in that early era. Both of those have become virtually unimportant in the modern understanding of the universe, mostly because the light's been diluted and the curvature has led to a universe that's so large that it is essentially flat. In fact, it is, from a geometric point of view, you can describe the universe by using the same equations that we learned in middle school. Euclidean geometry works in our universe. Our universe is geometrically flat. Now, we make the point that geometry and shape are not the same. So the universe has the geometry of the universe has been measured, and to within a tiny, tiny fraction of uncertainty, it is geometrically flat. Any triangle you draw in our universe, no matter how large, will contain 180 degrees. Circles, huge circles that you might draw, have a circumference that's 2 pi times the radius, and so forth. As I say, we all learned this in our teen years when we studied Euclidean geometry. So we now know that the sum of the density of matter, omega m, and the dark energy density, omega lambda, equal 1, and 1 is important here. That is the universe that was originally defined by Einstein as in his equation. So if omega m and omega lambda equal 1, we are right on the edge of what is called the critical density of the universe. And here's the kind of result you get for both, here's now, and for both the past and the future. This is how the energy densities influence the size of the universe. Now, size for astrophysicists means how does the distance between galaxies grow or shrink? So here we are. Of course, there's a phone call. I'll deal with that later. So if the universe was not at the critical density, but was at a density of 6 times bigger than the critical density and was all matter, the universe would have grown and then would collapse. So that's what this arc represents. If the universe was at the critical density and exactly equal to 1 and was all matter, then the universe would just continue to grow along this dotted trajectory. And then we have a possibility of the universe is less than critical at 0.3 and all matter, still growing, but it has a different geometric property. But this is the one that we have observed, that 30% of the universe is matter. And remember, that includes the atomic stuff that we are, and mostly dark matter, and 70% dark energy. And you can see this version of the universe has this growth to it. And that represents the accelerating expansion that was first observed in the late 1990s. So that's the key one right there. Now, Hubble, Edwin Hubble, for whom the Great Hubble Telescope is named, he measured the expansion of the universe back in the 1920s. And here we have distance and velocity, and his data collected from the ground from a relatively small telescope gave him this relationship between distance and velocity. We now know it's more like this because we have modern data. Nonetheless, he opened the scientific eyes of the world to the idea that the universe must be expanding because more distant objects are going away from us at higher speeds than closer objects. And this line comes from type 1, a special type of supernova, usually measured using the Hubble Space Telescope, named after Edwin Hubble. Over the years, the Hubble parameter, or the Hubble constant, has been measured over and over. Here we're back in the 1920s and 30s. These are numbers that Hubble collected working with older technology, and his numbers were much higher. The expansion rate he predicted was much higher than the modern value, and you can see over the years, we gradually homed in on a value here. We're not done yet, however, and I'll explain why in a second. So back in the late 90s, Adam Riess and his colleagues, who later won a Nobel Prize for this work, showed that supernova events plotted on a similar curve to the one I showed over here, that these events appear in this blue part of the curve. And any event that appears in the blue part of the curve indicates that the rate of expansion of the universe is accelerating. We have a few examples that are just barely into this pink area, which says the universe is expanding, but the rate of expansion is decreasing. But the bulk of the data that's been collected, and much has been done since the late 1990s, continues to show that the universe is not only expanding, but its rate is accelerating. Now, let's see how that compares with what's been observed. So here we're using a terminology astronomers use called redshift. Not important to worry about that, but it's a way to look back into the past. So zero redshift is now, and redshift numbers, say of 3, means we're looking back 11 or 12 billion years. And all these black dots and red dots and green dot and so forth are measured positions of various kinds of astronomical events, and they imply this number, which is related to the Hubble constant. So we have various possible measurements, and the one that I mentioned already, when we use omega m and omega lambda of 0.3 and 0.7 respectively, we get this green curve, which lies right on top of the bulk of the data that's been collected. So we have high confidence that we understand the ancient history of the universe. Remember, this graph is showing what we see in the past by measuring properties of receding supernova events. There are other lines. These thin lines show you what we would have gotten if the universe was split 50-50 between matter and dark energy, or 40-60, or 20-80. The one that works is the one we actually measure, 30% 30% matter and 70% dark energy. So there's no question that we're on the right track. We're plotting right through all the measurements, and measurements of all different types. Nonetheless, this does not explain what dark energy is. It just says that we have measured the proper value. And you can see there's a minimum here. I mentioned this earlier, that the ancient universe was expanding at a higher rate than it is now, and that gradually, that higher rate descended. Remember, we're looking back in time here, and right about here, about 7 billion years ago, the expansion rate, which had been falling, started to increase. And we now understand why this increase occurred. This falling part of the curve resulted from the influence of matter in the universe, gravitation between the matter in the universe was retarding the expansion. But eventually the universe got big enough that the density of matter was diluted so dramatically that dark energy could assert itself. And now we're on this upward trajectory of a higher and higher expansion rate, and that will continue forever. So let's take a little more detailed look at this before we get into at least one of the theories that might explain dark energy. I've already said that the dark energy that's being produced as the universe gets bigger overcame the retarding influence of matter about 7.5 billion years ago. It's roughly half the age of the universe. And we expect dark energy to dominate going forward. So let's look at a graphical presentation. This is the curve I just showed you. That's looking backward. So here's the present, and here we're looking back 12 billion years. Now let's look forward. Using the models we have and the data we've collected, now we're looking at, this is now, and this is the future, say 100 billion years from now. So once again, we see that the universe was expanding at a decreasing rate. Now, let me emphasize, the universe has never gotten smaller in its history. It's the expansion rate we're looking at. So it's like if you decide to go on holiday and visit your mother-in-law, you never turn around and come back. You're always progressing toward her house. You may go at a different rate because of traffic or weather, but you're always progressing toward your target. And that's what's going on here. The expansion rate was decreasing until about 7.5 billion years after the Big Bang. Then it started expanding, and this red dot shows you where we are now. This is 13.8 billion years of expansion of the universe. And we expect the expansion to accelerate for the rest of the life of our universe. So this is a major problem, explaining why there's dark energy. And I mentioned that we measure it by measuring the Hubble constant. And here's the history of that progression of understanding. Back in the early 2000s, we had multiple ways of measuring the Hubble constant. And the error bars were pretty big, and everything was in this cloud of results. And you see the number here. It's a technical number. You can look it up and you'll see what this means. But the average was about a number of 72 in those technical units. As we got to a period about 10 years ago, different techniques began to show different results because the error bars got smaller. And right in this region, say 2012 to 2014, we realized the average is not the way to do this because each technique produces a different result. The blue here is the result from supernova events. You see the blue dots, and the average of that is right here at around 73. Meantime, something called the cosmic microwave background provided data. Those are the red dots, and it settles in on a value of about 67. This is a mystery why these two numbers are this far apart. And because of the frustration of what is called the Hubble tension, that is that the errors are so small, we can now see the different techniques are producing graphically different results, 10% difference, which is huge. A new technique called this red giant branch technique was invented, and it produces, unfortunately, it produces a value right between the two prior techniques. So we're struggling with this, and a Nobel Prize awaits for somebody who can explain why we get different results from different techniques. And there's some detail here I'm not going to go into right now. And even more detail here on the so-called Hubble tension. You see it right around here. People realized, wait a minute, this group of supernova results that rely on variable stars called Cepheids, that's giving a very different results than the cosmic microwave background. And the tip of the red giant branch gives a number right in the middle. So we're just struggling with that. Now, let's switch from astronomy to quantum physics, because maybe that's an explanation for this mysterious dark energy. And we have to introduce Louis de Broglie, who in the 1920s postulated a theory that everything has wave properties. And we'll see in a second why this is important. We knew that electromagnetic radiation, for example, has wave properties, but he said not only does light and radio waves have wave properties, but matter has wave properties. And the wave property is related to something called Planck's constant, which was invented in 1900, and the momentum of an object. So according to de Broglie, an electron, which has momentum because it's been produced in some kind of electron gun, has a wavelength. This was a revelation. This is the 1920s that he brought this up. And modern experiments confirmed de Broglie. And he, in fact, soon after he made his prediction, the wave property of matter was detected, and he won the Nobel Prize. And here's an example of what we see. We fire electrons into a crystal. And what do we see? We see these alternating bands of bright and dark that are usually associated only with wave properties of light. And yet electrons produce this picture by scattering electrons from a crystal. And so we have demonstration that de Broglie was right. In addition, Heisenberg said, if you try to measure quantum properties and you measure the energy very accurately, to do so requires more time, delta meaning a variation, and that the product of these, of an energy measurement and a time measurement, has to come out to be something like Planck's constant. And that bar just means it's Planck's constant divided by 2 pi. So de Broglie and Heisenberg began to understand in the 20s and 30s that there is wave property of material, and that the confining a measurement of energy takes a long time. But if you take a short look, a brief glimpse at a vacuum, for example, you might see large energy, as long as these two products multiplied equal Planck's constant. Now, let's introduce yet another person. Oh, well, first we're going to say that what de Broglie and Heisenberg predicted was, if you have an empty space, you would see this kind of spontaneous emergence of quantum particles that appear and disappear in extremely short periods of time. This is sometimes called quantum foam, that every volume of space is just surging with light particles, matter particles, and the heavier they are, the shorter their life is. And there's no energy invested in this. It just happens spontaneously because of the wave properties of matter and Heisenberg's uncertainty principle. Now comes Casimir. At the end of the 1940s, tremendous progress had been made in understanding the subatomic world, and Casimir had an idea. He said, if light spontaneously appears in a vacuum, let's do an experiment. Let's take a box. Let's take all the atoms out of the box. It will be filled with a foam of quantum fluctuation, particles and light. And then let's put 2 plates into that vacuum and put them very close together. The closer together we put them, the fewer light particles can fit between the plates. The wavelengths of light have to be such that they will fit in here. Otherwise, when this happens, there should be a force, a measurable force between the 2 plates, because out here we have all wavelengths bumping into the plate. And over here, we have all wavelengths bumping into this plate. But in between, we only have the shortest wavelengths, so there should be a net force between these plates. This is called the Casimir effect. And when he predicted, and I'll show you his calculation in a second, when he predicted the force between the plates, his colleagues thought he was crazy. So 2 plates carefully balanced, we should be able to measure that force. This is in the late 40s. Particles like electrons and neutrons and so forth that spontaneously appear in the experiment, they don't influence the result because their wavelength is so short that they easily fit between the plates. So a virtual, the words used is a virtual electron that appears in here wouldn't affect this because there are virtual electrons everywhere in the experiment equally balancing the force on the plates. But electromagnetism would not be in balance. So over here, I have a little detail how big the wavelength of an electron is. It's way smaller than the distance between the plates you need to actually make this measurement. In the late 40s, the experiment could not be done. It was too technically difficult. However, we could predict the results, and this is what Casimir did. I'm going to show you how to calculate the result without using very much math at all, just a little arithmetic. We can assert that this simple experiment would rely on just a few things. Anytime there's a quantum effect, we have Planck's constant. And the speed of light, it would certainly be a factor here. We're talking about electromagnetic radiation. And then we have the distance between the plates. So let's do dimensional analysis. And let me give you a simple example of dimensional analysis. You may have seen this during your education. Let's use dimensional analysis to predict the law that describes the period of a pendulum. What are we dealing with here? We have the length of the pendulum, which has units of length. We have some period, we'll call this the period, the time of oscillation, or the period, units of time. We could put a mass on the end of this that has units of mass, and the gravitational influence of Earth, where we are going to use this pendulum. And if you do a little arithmetic, you will find in just a minute or two, the only way to get time out of this, and this is this result, the square root of the length over Earth's gravitational acceleration. And in fact, the mass on the end can't matter. So this is a simple case of using dimensions to get a technical result. Now, this result is correct to within a factor of 2 pi. We don't get exactly the right answer. You have to do physics to do that. Notice we didn't do any physics here, except we picked the right parameters to work with. But we do get the scaling law. We get that if you make the pendulum length longer, the period of the pendulum depends on the square root of the length. Or if you take the pendulum to the moon, where the gravitational constant is much smaller, you get a different period. So we get the scaling law, but we don't get this 2 pi. Now, we're ready to go on and do the same thing for Casimir's experiment with the plates. And we've already agreed, Planck's constant has to be apart, the speed of light has to be apart, and the separation of the plates has to be apart. So we have these units. I have to tell you that Planck's constant has these units. Speed of light is length over time, and the spacing of the plates is this. And we want to calculate, as best we can, the pressure that would be felt between the 2 plates in the Casimir experiment. That pressure is force divided by area, and it's going to be negative because he asserts that the plates will be forced together. So the question is, if we raise Planck's constant to an exponent and the speed of light to an exponent and the distance between the plates to an exponent, and do the same thing to these units that we have, we can get 3 equations. Why? Because force over area is mass to the 1 divided by time squared and length to the 1. And we get from here, by collecting different terms like length squared to the A and length to the B produces this, and to D, we get this group of exponents. So by collecting exponents and knowing the units of pressure or force per unit area, we get 3 equations, one for time, one for mass, and one for length. and we do the arithmetic, we get these three numbers. So we conclude that the force per unit area in Casimir's experiment should be proportional to Planck's constant times the speed of light divided by the distance between the plates to the fourth power. And so that gives us the scaling law. We are missing the multiplier here. I'll show you how that's done in a second. So we have the scaling law. In fact, Casimir did the calculation using very advanced mathematics, and he gets this. Well, there's Planck's constant, and there's the speed of light. We got that. And here he used A for the separation. And it goes as the fourth power. So we got the right scaling law, but we were missing this pi squared and this 240 and so forth. But nonetheless, we're on the right track. And an appendix to these charts provides the arithmetic necessary to get this result. Now, modern day, this is a modern day picture of how the Casimir experiment is done. They use two tiny glass beads coated with gold, and using a microscopic pendulum, they measure the force between them. That's what's represented here in orange. So people are still doing this experiment. It took 50 years to do this experiment. And here's the result they got. These little squares represent measurements. Notice the separation of the plates is on a scale of hundreds of nanometers, billionths of a meter. Here's the curve that was predicted by Casimir. So sure enough, the results, which took 50 years to develop, agree. So Casimir is getting the same results. He's calculating the energy in empty space. That's what his experiment deals with. So it took 50 years to do this. So hallelujah, the physicists have measured the Casimir vacuum energy. And I use this picture because that's the university I went to. So hooray, the physicists have measured vacuum energy, and the astronomers have measured the cosmological constant, or dark energy. And these two things should be the same, correct? Well, they're not the same. There's a tiny difference between them. And that difference is so tiny, it's 10 to the 120th, which is not tiny. I'm being sarcastic. And you can find quotes everywhere in the professional literature. This is the worst prediction in the history of physics. The physicists thought they could explain dark energy by going in the lab and doing the Casimir experiment. And the astronomers say, we've already measured vacuum energy, and we know what it is because we can see how stars move. And they're not the same at all. It's a stupendously different number that they get. And there's good news. The astronomers are right, because if the physics number was correct, the universe would have expanded so rapidly that we would not be here to observe it. Stars would have never formed, galaxies would never have formed, heavy elements would never have formed, and we would not exist. So fortunate for us, the astronomers have it right. The question is, why does empty space have such a tiny vacuum energy? Why isn't it zero, in fact, is a key question. And the physics people haven't been able to make a contribution to understanding why the universe has picked a very, very tiny, but not zero, vacuum energy. So I say, this is good news, because if the measurements at the university were right, we would not exist. Oops, something got. Huh? So this is the end of our formal presentation, and here's our conclusion. We have used astronomy, quantum mechanics, dimensional analysis, and some math I'm going to show you because we have a few minutes left. And we've tried to answer the question, what is dark energy? And we're frustrated. We don't know. It's not the same as the vacuum energy you measure in a laboratory, but we all love a challenge. And so we're not done. Everybody is looking for what is the real answer. Now, let's take a look at Casimir. And we might end a few minutes early so we can entertain questions. I see some questions popping up. So Casimir exploited this kind of feature. He, in his calculation, dealt with the difference between the sum of a sequence of numbers and the integral of the sequence of numbers. Some of you will remember this from college days, or perhaps you do the work with these kinds of things professionally. These things do not generally give the same result. For example, if you sum these integers set up this way from 1 to infinity, you can do this calculation. It's a series of numbers. It starts with a larger number and gradually gets smaller, and the sum is equal to 1. But if you do the integral of that same kind of function, you see the parallel here, from 1 to infinity, and do the arithmetic, you get a different number. You get the natural logarithm of the number 2. So that just exploits this factor that Casimir was working with. And for Casimir's experiment, he showed that the pertinent function is this. It's a pi over 4, and then x cubed, and an exponent with x in it. And whatever result you get, you have to let this number here go to 0. Now, he also exploited an invention from the early 1800s called the Abel-Plana summation formula. I won't go into detail here. Those of you who have a background and have dealt with complex numbers maybe want to chew on this. So the Abel-Plana number with this function leads us to the following calculation. And once again, I won't go through this. If you're interested, you want a little challenge, you might work your way through this and then the second page of it here. And if you do that, in fact, you get the multiplier that Casimir got. Once again, we found the force per unit area proportional to Planck's constant, the speed of light, and the 4th power of the separation of the plates. We didn't get the coefficient that goes here. Casimir got that coefficient and he got it right. This is what he got. Ignore this 27, that's the page number. So we all agree, Mother Nature is happy with this. Now I do want to show you a little, I want to show you a little oddity. Casimir didn't do the problem exactly like I just showed. Did it a bit differently, and he relied on something called the Riemann zeta function. And he got the same result I just showed you. Here's the definition of the Riemann zeta function. It's either a series or this integral. Here's the Riemann zeta function. It's been calculated many different ways over since 1840s when Riemann did his work. So the Riemann zeta function for the number 2 is 1 plus 1 over 2. Let me refer you to this first. The zeta function is 1 over a number raised to a power. So if you want the value of the zeta function for the number 2, it's 1 plus 1 over 2 squared plus 1 over 3 squared and so forth. And a formal analysis gives you pi squared over 6. If you want the number for Riemann of number 4, you do the same thing, 1 plus 2 to the 4th plus 3 to the 4th, and you get pi to the 4th over 90. Casimir used this value, the zeta function evaluated for the number -3. And from that, you get the Riemann function equals 120. Now, I'm going to remind you that Riemann's result is correct. Nature, when we go in the lab and measure it, nature gives us a result that matches his calculation. But now let's look at what is the formal definition of the zeta function for -3. It's equal to 1 plus 2 cubed plus 3 cubed plus 4 cubed. Now we would all agree that there's something weird going on. because 1 plus 8 plus 27 plus 64 is most certainly not 1 over 120. It's a big number. And this is one of the weird oddities that go on when you use series in doing mathematical calculations. These are called indefinite sums, and I have a reference for those of you who want to talk about these things or read about them. So we have relied on the Riemann, or Casimir relied on the Riemann zeta function and got the right answer. We know that because the laboratory results match his theory, and yet we're dealing with this crazy result that the sum of cubes equals a fraction less than 1. What's even weirder, and comes from a modern theory of the world called string theory, is that the Riemann sum for the number -1 is the sum of integers. It's 1 over 1 plus 1 over 2 to the -1 and so forth. And that equals -1/12. And so I just want to introduce you to these mathematical oddities. Here's a derivation done by the famous Indian mathematician Ramanujan back in the 1920s, where he manipulates it. You have to read through this page to see it, but he manipulates sums. And by just shifting and subtracting, he gets the result that the sum of the integers is equal to -1/12. So it's a weird world out there in the mathematics. In fact, here's a famous string theory book by Polchinski that makes a point that the sum of the integers equal to -1/12 is a central mathematical result used in string theory. So, I'm going to close with this. Consider this sum of the alternating sum, 1 minus a half plus a third minus a fourth. You can show that that's equal to the logarithm of 2. But now if you rearrange the terms, if you say 1 minus a half, group them together, and minus a fourth, and then group together a third and a sixth, and you see what I've done here, and redo the sum, you get a half minus a fourth plus a sixth. Well, that's what you started at, except multiplied by a half. So what we end up with is one version of the sum equals logarithm of 2, and the other equals 1/2 the logarithm of 2. This is the weirdness of infinite sums. So I'm going to skip ahead and show you a book. Hang on. This book is available. You can find it online. It's out of print. Divergent series. You might want to look at that. And now let's stop the lecture and go to questions.
Thanks very much, Ed. It's a lot of food for thought there, and I can see that there's at least 8 questions waiting for you. Just encourage the audience, if you have a question for Ed, please put your question in the Q&A panel at the bottom of Zoom, and we will now move on to the Q&A section. That'll be hosted by my colleague George Williamson. So George, I'll hand over to you to put the questions to Ed, please.
Right, thank you very much, Ed. First question we have is from Eric, and he asks, could dark matter and dark energy be related to one another by E equals mc squared?
Well, since we don't know what either one of them are, the answer has to be yes. Could it be? I don't know. Nobody knows. Right now, the dark matter influence, particularly on the formation of galaxies, has been well defined. And we understand that dark matter is about roughly 27%, or sorry, 22% of the universe. But could it be that it's somehow related to the fact that dark energy, which is related to the expansion of the universe and is about 70%, could they be related? Yes, they might be. I don't know. All right, I think we're ready for the next question.
Okay, question from Colin. Is the gravitational constant dependent on the density of dark energy?
As far as we know, Newton's gravitational constant is related to dark energy, almost certainly, but the gravitational constant has been constant through the life of the universe. This is the best way I can attack this question, is when we look at and predict what we will see, and we've done so successfully using models derived from Lemaitre and Friedman, always the gravitational constant is always taken as a constant, but the density of dark energy has changed over the life of the universe. In the early universe, it had no influence at all. Now it's very influential. It's driving the expansion. And yet over that whole time, we think that Newton's gravity constant has been the same. Now, that might not be true either. It's possible that, and people have certainly explored this with not much success, that maybe Newton's constant for gravity has been changing over the eons, and that explains dark energy. So far, I don't know of any successful theory that matches observations based on that approach.
Right, okay, thanks, Ed. Question from Chris Hale, which I think plays into two of your areas of background. If the universe is expanding, doesn't that make navigating it difficult? I would take that to be more local navigation of the universe, maybe the solar system.
Yeah, so one thing I did not emphasize, and we can talk about very briefly, is that locally, for example, in our solar system, in our galaxy, in nearby galaxies, the expansion of the universe is virtually zero. You have to be looking at the vast expanse of billions of light years of distance before the influence of dark energy is seen. So for example, the dark energy propelling expansion of the universe does not impact at all the size of atoms, because atoms are totally dominated by the electromagnetic connection between electrons and the protons in the nucleus. The orbit of Earth is not influenced. The gravity, local gravity, is totally dominant. You can never detect expansion of the universe locally. So it's the navigation here on Earth, or even navigation between the stars, is completely not influenced by the expansion due to dark energy. You have to be looking at objects billions of light years away to see it now. And that, by the way, that explains something about the big error in Hubble's original measurements. Remember, I showed that his number was dramatically bigger than the number we accept today. And part of that was because he couldn't see that far out into the universe. What's more, some local, like Andromeda, galaxy Andromeda, is coming toward us. It's not moving away, because the gravitational attraction between Andromeda and the Milky Way is way bigger than the very tiny dark energy effect. Remember, I mentioned dark energy is extremely tiny. You can only see it on a cosmological scale. Okay.
Thank you, Ed. From Chingman, if due to Big Bang the expansion is omnidirectional, is it possible to observe the universe from the galaxy expansion and direction to estimate the center of the Big Bang?
And the answer is no, there is no center. So usually we rely on an analogy with, imagine a balloon and put some little stickers on the balloon that represent galaxies, and now inflate the balloon. No galaxy on that surface can claim to be the center. Everybody sees other galaxies moving away from it. If you put raisins into a raisin bread and put it in the oven, the dough gets bigger as it bakes, and every raisin sees others moving away from it. So there is no center. And as I said, we don't know the shape of our universe. We only know the geometry. But no, this you can't detect the center. There is no center. Everything is moving away from everything else. Okay.
Thanks, Ed. A question or maybe some kind of statement from Ed L, which you may want to comment on. The assumption that the universe will carry on expanding at an ever increasing rate due to the influence of dark energy cannot be stated with certainty, surely. In physics, we're not currently aware of may in future lessen the impact of dark energy. Therefore, the possibility must still remain that the ultimate fate of the universe will be to either still expand at a lesser rate, become static, or indeed contract.
Yes, what he says is absolutely true. I should have said, based on what we know today, the universe will continue to expand. But let me throw this at you. If I showed one graph that goes out to 100 billion years of life of the observable universe, eventually this will be an unanswerable question, because the expansion will mean that the galaxies we use to observe the expansion will have receded from us to a point where they're no longer visible. They will be redshifted to a point where we will not be able to detect their light. And when that happens, future astrophysicists will have nothing to rely on to understand the expansion of the universe except the stars in the Milky Way, or possibly the stars in the galaxy that results from the Milky Way and Andromeda combining. There won't be any other galaxies to observe. So it's possible that Ed is correct. Future astronomers will not be able to understand the origins of the universe. They will not see the microwave background. It will have been so far redshifted that it'll be undetectable. And galaxies will have disappeared. Now, could those galaxies re-enter the observable universe of the far, far future? Yeah, that could happen if there's some other physics involved, or if the geometry of the universe changes. But yeah, that's a deep question. But based on what we know today, the universe will continue expanding at an accelerating pace. Okay.
Question from Neil. The simple question is followed by a statement about a particular set of conditions. He says, if the experiment with the plates is done in space, would the result be different? And he suggests that it be that the amount of space foam is influenced by the amount of matter present, leading him to the conclusion that the speed of light may be the part of the equation that doesn't quite work, perhaps because time is a function of probability rather than a constant.
Okay, well, first sentence first. If you did the Casimir experiment in space, remember that the vacuum fluctuations that Casimir correctly predicted, are 10 to the 120th times bigger than the energy that empty space out in the cosmos has. So the Casimir experiment done in empty space should result in exactly the same value we get in the laboratory, because the quantum fluctuations are so much bigger than the dark energy we observe. And so speed of light, yeah, that's possible. Speed of light might change over the life of the universe. We do not see any such effect in observations we've made so far. Let me just stop real quick. I see a lot of questions that we're perhaps going to run out of time. I know my hosts are going to collect the questions, and as we did last time I spoke, I will write answers to all these questions. So don't be alarmed if we don't get to your question in this conversation. I will send the hosts question and answer document that you can all peruse. So should we do a couple more?
A couple more, yes. Where do wormholes fit in with dark energy?
Well, we don't know how to produce wormholes, and we don't understand dark energy, so I don't know how to answer that.
From Ian B, the search for dark energy seeks to explain the observed expansion of the universe. Do we have any handle on the physical cause of inflation in the early universe?
Yeah, so what Ian's referring to is an event that occurred in the, so let me stop and introduce a constant. It's called a jiffy, Jiffy. I think a jiffy is 10 to the minus 23 seconds. So Ian's referring to an event proposed to have occurred in a jiffy, something like that, or maybe a jiffy, 10 to the minus 46 seconds, that took the universe from a infinitesimally small primordial atom to something dramatically bigger in virtually no time. And inflation is a model that matches observed properties of the cosmic microwave background, but that doesn't explain what inflation is. And Ian refers to the physical cause of inflation. No, we don't know. We have a mathematical description of what could have happened, which is a good thing, but there's nobody has a reason why inflation occurred. And there's people constantly attacking inflation as having some serious fundamental issues. Nonetheless, it does explain what we observe when we look at the cosmic microwave background. Perhaps I'll get invited back sometime to talk about the cosmic microwave background.
From Steve Cudahy, so from this, we're looking at a traditional heat death scenario of an expanding universe. We could be looking at an infinitely wide universe that still retains energetic functions it currently has.
Well, heat death is a descriptive term. I would describe it as a heat death. Eventually, the universe will be, unless you're in a local region like a galaxy or near a star, the universe will be really cold. Right now, the average temperature out there is 2.7 Kelvin, and the temperature is going down as the universe gets bigger, and eventually it'll be unpleasant if you're out there without the protection of a planet and a star.
I think this is probably a good one to finish with the formal questions live. It's from Barry, and he suggests that sadly, we will never be able to resolve this problem because we will need to make observations billions of years in the future to compare with theory. And since species on average only survive for a few millions of years, we may be doomed to be and remain ignorant as we won't exist that long. So any thoughts? Any observations?
I'll close with this. It's a perfect question to end with. This is a good time to be an astrophysicist because 20 or 30 billion years from now, you won't be able to do any cosmology. You'll be able to do galactic physics by looking at your local environment. But Barry's absolutely right. Unless some new physics emerges, we will never solve some of these problems because you have to wait billions of years to see how this giant void that we live in will continue to evolve. So thank you for that question, Barry. I have more to say about that in the written responses, but I think we're out of time. And I thank you all for your patience and listening to me. I know some of this was perhaps for some a little mathematical, but nonetheless, it is a part of the history of cosmology to try to understand why the quantum measurements proposed by Casimir do not explain what we observe out there in the cosmos. And I hope some progress is made in my lifetime. So we better hurry up because I'm pretty old. So once again, thanks to everybody. I look forward to talking to you again sometime in the future. And I think I'm done. And can you just make sure that I get the chat as well as the questions?
Okay, we'll try to do that.
Thanks very much, Ed. That's a truly thought-provoking presentation, and I think I'm going to have to review the video recording of the presentation to get my brain back into some of the maths that I should know. But great presentation. Thank you, and
Thank you so much.
Thank you to the audience for some great questions as well. Ed, I know you've put a lot of effort into bringing that presentation to us, and I really thank you. And rest assured, we'll be inviting you back for the next chapter in your wonderful lectures. So thank you so much.
Okay, thanks to everybody, and have a good evening.
And just before we go, just a few admin bits and pieces. So just want to thank George for grouping the questions and asking them to Ed on behalf of the audience. And for the audience, I just remind you that we are recording the presentation, so that will be available in a short period of time. We have to do some post-processing on the recording, but as soon as we can, we will upload that. And as Ed said, he will provide written answers to a lot of the questions that have been posed in the Q&A and the chat. So very much appreciate that. I just want to move on to the next slide, actually. Just like to draw your attention to a couple of events forthcoming in the not too distant future for Anglian Coastal Local Network. On the 30th of June, we've got a presentation on space weather by Dr. Gemma Attrell, who's the space weather lead at DSTL. That will be a webinar format. And then followed shortly after that, on the 5th of July, 7 p.m. in the evening, we will be having a hybrid event. That will be a face-to-face gathering at the University of Suffolk, and it will also be an online event. So we call those hybrid events. That will be by Ronan Kelly from ADTRAN, and Ronan will be talking about a fibre foundation for the next 100 years. So we'll be looking at fibre access and fibre networks. So a couple of very interesting events coming up. If you're interested in those events, further details will be available on the link at the bottom of the slide here. I think we've got the registration up for the 5th of July event. We need to do a little work to bring the registration up for the 30th of June event. There's a bit of admin to do on that, but the 30th of June event will shortly be available. Also, CPD certificates for today's event and previous events are available on the engineering community's site. So if you go to that link on the slide, you should be able to get your CPD certificates. So with that, finally, on behalf of the Anglian Coastal Local Network, thank you all for joining tonight, and a big thanks to Ed for putting on such a fascinating presentation, and I'm delighted to see the audience participation in the questions. So thank you very much, and thank you to the IET team and local network and Julie who put on tonight's webinar. So that concludes the webinar. You may disconnect now. Thank you.